This is naive recursive Fibonacci, and it is painfully slow. To find fib of 5, it recomputes the same values again and again. For fib of 50, that is billions of wasted calls, and your program hangs. But one tiny change makes it instant. Solve each subproblem once, remember the answer, and reuse it. That is dynamic programming. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and data structures, visually explained. 23 of them, each a clean diagram and runnable Python. Dynamic programming is in there too. $24, link below. Totally optional. Now, let us make slow recursion fast. First, why is naive Fibonacci so slow? Watch the call tree for fib of 5. Each Fibonacci number is the sum of the two before it. So fib of n calls fib of n-1, plus fib of n-2. 2 calls, every time. Fib of 5 calls fib of 4 and fib of 3. Fib of 4 calls fib of 3 and fib of 2. But look, fib of 3 is already computed twice. Go deeper and it gets worse. Fib of 2 shows up 3 separate times. Fib of 1, 5 times. The same subproblems are recomputed again and again, in branches that never share their work. The tree does not grow. It explodes. Every level roughly doubles the calls. That is O of 2 to the n, exponential. Fib of 5 is 15 calls. Fib of 50. More calls than seconds in your life. Those repeated subproblems are the whole problem, and the whole opportunity. Dynamic programming works whenever a problem has 2 ingredients. Miss either one, and it does not apply. Ingredient 1. Overlapping subproblems. The same smaller problems come up again and again, exactly what we saw with fib of 2 and fib of 3. If subproblems repeat, you can compute each one once and reuse it. Ingredient 2. Optimal substructure. The best answer to the big problem is built from the best answers to its subproblems. Fib of n is just fib of n-1 plus fib of n-2. The whole is made from its parts. When both are true, dynamic programming applies. And it comes in 2 flavors, top-down memoization, and bottom-up tabulation. Let us see both. First, memoization, the top-down fix. Top-down means you still write the natural recursion. But you keep a cache. A little memo pad. Before computing fib of k, you check the cache. Seen it before? Return the stored answer instantly, in O of 1. Never seen it? Compute it once, then write it down. Watch what that does to the tree. The first time we reach fib of 3, we compute it and store it. The second time, it is already cached, so this whole branch collapses to a single lookup. Same for fib of 2. All those duplicate branches vanish. What is left is one computation per unique value, fib of 0, 1, 2, 3, 4, 5. The exploding tree becomes a straight line. That is O of 2 to the n collapsing to O of n. Each Fibonacci number, computed exactly once, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Memoization works from the big problem down. Tabulation flips it, bottom up. Instead of recursion, you build a table from the base cases up. Make an array, dp, set dp of 0 to 0, and dp of 1 to 1. Those are the base cases. Then fill forward. dp of I equals dp of I minus 1 plus dp of I minus 2. 2, 3, 5, 8, all the way up. No recursion, no call stack, just a loop filling a table. When you reach dp of n, that is your answer. Same O of n time. And here is a bonus. To compute dp of I, you only ever need the last two values. So keep just two variables and throw the table away. That drops the memory from O of n to O of 1. Fibonacci is the classic. But dynamic programming is far bigger than one sequence. Take coin change. You have coins of 1, 3, and 4. You want to make 6, using the fewest coins. Same idea, solve it for every smaller amount first. Let dp of a be the fewest coins to make amount a. dp of 0 is 0, 0 coins make nothing. For every other amount, try each coin and take the best. dp of 1 is 1. dp of 2 is 2. dp of 3 is just 1, the 3 coin. dp of 4 is 1, the 4 coin. dp of 5 is 2. And dp of 6. Try a 3, leaving 3, which needs 1 more coin. That is 2 coins total. The table reads 0, 1, 2, 1, 1, 2, 2. The answer, dp of 6, is 2 coins, 3 plus 3. Overlapping subproblems, optimal substructure. Dynamic programming, again. Here is bottom-up Fibonacci in real, runnable Python. It is shorter than you would guess. If n is less than 2, return n. Those are the base cases. Otherwise, keep two variables, previous and cur, starting at fib of 0 and fib of 1. Loop from 2 up to n. Each step, slide the window forward, the new pair is cur, and previous plus cur. When the loop ends, cur holds fib of n. No recursion. No exploding tree. O of n time, O of 1 space. The same fib that hung your machine now returns instantly. Let us lock it in. Naive recursion is slow because it recomputes the same subproblems. Fib of 5 is 15 calls, and it only gets exponentially worse. Dynamic programming fixes that when a problem has overlapping subproblems and optimal substructure. Memoization is top-down. You recurse, but cache each answer and reuse it. Tabulation is bottom-up. You fill a table from the base cases up, and often shrink the memory to constant. Either way, you solve each subproblem once. That single idea turned O of 2 to the n into O of n, solve it once, write it down, reuse it. So that is dynamic programming, the fix for slow recursion. Solve each subproblem once, remember it, reuse it. Next in this series, we move to graph algorithms. BFS and DFS, breadth first and depth first search. The two ways to explore any maze, any network, any social graph. If you want the whole picture, 23 algorithms and data structures, each a diagram in clean Python, my book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.